All right, so the first Millikan oil drop question. You have an oil drop with this mass experiencing a downward acceleration. Calculate the electric force. Okay, so when you're talking about Millikan oil drop experiment, this is always the case. Fg equals Fe. Okay, what we're given here is we know the mass and we know the acceleration. So the net force here is equal to ma, right? Net force is always ma. So if we know the mass and we know the acceleration, it says it's experiencing a downward acceleration. In this question, can we say here that the net force is 0? Yes or no? No, it isn't, right? What is the oil drop doing? It's falling down. Is it falling down at 1 G? It's actually falling down at more than 1 G, right? It's more than 9.8. It's falling down faster than at a regular rate, right? So the net force is not 0. In this case, the Fe is not equal to the Fg yet, right? So again, if you're doing this experiment, you're going to need to adjust your electrical field strength to make the oil suspend and not fall down. Why do you think this is actually falling down faster? The charge is what? Something is happening here, right? So you got these two parallel plates. If the oil is suspended right here, what do you want the parallel plate on the bottom be? So that it actually gets the Fe going up and the Fg going down. What do you want the charge on the plate? On the bottom. You want it to push up, right? So the electric field lines then has to be going up, so the plate on the bottom should be positive to do this correctly, to suspend it, right? So with the negative at the top there, so the Fe, see the electric field then, the electric field lines will be going this way. So it's the balance of those Fe and the Fg, right? So in this case, the plate must be what on the bottom? It's gotta be positive at the top here in this situation, right? Does that make sense? So what you got here is, here's the oil droplet. Yes, it will fall down with the 1G because you got Fg. But now you have this electric field lines that are actually pushing down the oil even more. Does that make sense? So the oil is now attracted to go down. So your net force here is actually Fg plus Fe, okay? And it is not 0. It's not equal to 0. These two are actually working together to push the oil droplet down. That's why you're accelerating down, okay? So to get the electric force here, all you need to do then is to basically find the mass and it's accelerating down. That's all we need to do for this one. So what would that be? So 4.95. Does anyone have a calculator? Multiply this by 18.4.
So 9.1 to the power of 10 to the 14. Negative 14.
Negative 14 newtons. There you go. That is the net force. Oh, it says calculate the electric force. How do we calculate the electric force now?
F net minus Fg.
Okay, so we go to this equation because this is what's happening. Okay, so the electric force then will be F net minus Fg, right? So we just calculated the net force there. So your Fe is going to be 9.1 times 10 to the negative 14. Take away, what's mg? Because mg is going to go down anyway with or without the electrical plates. So we actually needed to subtract the Fg from there. So we're going to go 4.95 times 10 to the negative 15 times 9.8. We have to subtract that. So the electrical force is...
So it ends up being in total 4.24 times 10 to the 14.
And confirm. Yeah? Close? Okay, so there you go. Take a look at, could somebody just calculate the FG? Or do you have it calculated? I'm just going to do it. 4.95 exponent negative 15 times 9.8. Okay, so this is the FG. This is the weight of that oil drop. 4.85 times 10 to the negative 14. The electrical force is 4.24 times 10 to the negative 14. It's less, right? So it's going to go down. All right. What about number 2? What do we have here? You got charge Q1 of 4 coulomb placed in an electric field between 2 charged plates. Let's identify the charges of the plates first. What are the charges of the plates? What's on the top and what's on the bottom? Okay. And you guys know that. Why? Because that is the flow of the electric field lines, right? Okay, so it's going up that way. Okay, awesome. All right, so now you put a charge between the 2 plates. Okay, it's 4 coulomb, positive. So this is a positive charge. The electric field strength is this, 5 newtons per coulomb. The mass of the charged particle, so this has a mass, is this. Determine the magnitude and direction of the acceleration of discharged particles between the plates. Okay. Okay, so what are the forces acting on our particle here? So you got your FG still down, right? Okay, and then what? So there's our particle there. Now, if this is a positively charged particle, where would it want to go? Up or down? Why? Because, okay, you got plates here. This plate is positive, right? If this is a positively charged particle, it's going to want to run away from the bottom plate. It's going to want to go that way, right? And that's what the electrical force would be directed to. Does that make sense? Remember, we go with the electric field line direction based on the charges, right? So what can we say here? So FG, is this 0? The net force is going to be 0. Where do you think it's going to go? It's going to go up. Okay. We can actually use the same principle that we did with dynamics here with the net force equation. So this is the net force is equal to F. If this is the positive, this is the positive, this will be negative. I'm going to go with the convention that we did before. So Fe minus Fg. And this is not equal to 0. Okay? So unlike the Millikan experiment where it's equal to 0 and the 2 forces are equal in opposite direction, this isn't. This is going to accelerate. It's going to accelerate up. Right? The particle will move upwards. Okay? We need to know where it's going. So that's where it's going to accelerate. That's where the net force direction is going to be. So we're looking for the acceleration. All right, so breaking it down, you got MA equals FE minus, I'm just going to actually go mg here. How do we break down the FE? Do we know the FE? Well, we don't, right? But we know electric field strength, right? So electric field strength is FE over Q. Okay, so FE then is equal to charge times the electric field strength, right? So we can then bring this over here. So MA is equal to charge electric field strength minus mg. And we're looking for A, right? So then we got charge, which is given 4, electric field strength, which is 5, minus mass, that's given, and g is given, divided by the mass. Okay, there you go, calculator work. So let's plug it in, okay? So charge is 4 coulomb. Just gonna put in the numbers here. Ignore the sig figs for now. And field strength is 5 minus mass is 1.75 times 10 to the negative 5 times 9.8 divided by the mass. And we know our acceleration, okay, which is 1.14 times 10 to the power of 6 meters per second squared. That's a big acceleration there. And you won't even see it. It will just be gone. It will just move up. Okay? Is that good? Any questions so far? Okay, so the most important thing here is we know what so things to know to answer a question like this is you should be able to identify the field lines and charge. Okay, so the field lines, those are the arrows. So by looking at the arrows, you will be able to know the charges, right? Positives go outwards, so this has got to be positive. Negatives go into it, okay? And then you put a charge there. You go, what is that charge gonna do in between these parallel plates? Well, it's gonna go up, okay? Once you identify that it's gonna go up, that's where the FA net would be, okay? And that would be the MA right there. Then we can figure out the net equation here and then solve for what we want. And those are the things that we need to know. All right, do we want to go look at the back? If you haven't had a chance to do this yet, do you need maybe 5 minutes to just figure out some of these questions? All right, question 5. I have an oil drop with this mass and balance in an electric. It doesn't say. Something is missing here. But what do you think is missing here? Electric what of this? Is that force or field? And how do we know? Electric field. And how did we know that? It's newtons per coulomb. We know it by the unit, right? So you could call it electric field. You could call it electric field strength. You could call it electric field intensity. So those are the words that you'll see. And again, the unit will tell you what that is. Okay, question A. Calculate the charge on this oil drop. So we're looking for the Q. All right, so again, we know Fe, electrical force, is equal to the Fg. This is charge, field equals mg. The negative sign is automatically there because of the Millikan oil drop. The point is to suspend it, so it will be in negative direction. So Q is the negative mg over field. Okay, so I think we got what we need. Do we know the mass? Yeah, we know the mass. Times 9.8 divided by a field of 4.36 times 10 to the 7. Okay, did we get the charge? Did we get this one here? Is that 1.85 times 10 to the negative 17 once we put it in the calculator? Okay, so that is the charge. Now, it says positive there. Why is that positive? An oil drop has this mass balance in an electric field. Calculate the charge. It's not talking about the picture above, right? Because that's number 4. So this picture, it says here, it is balanced in an electric field. Why would you say negative, positive there? We don't have any indication that it will be positive. Because if the oil is balanced, and you've got your Fg balanced by the Fe, could it be possible that you can do this with the plates being negative on the bottom? You can, but you're gonna need to make the oil drop bigger, right? With a lot more Fg. So, all right, so this should be The Q cannot be positive because we don't know.
I think the way he explained it to me was like he used the diagram from number 4.
Yeah, if we use the diagram for number 4, if you use the diagram for number 4, then this will be positive here, right? And these are negative. Okay, so then your net force, Fg electrical force here, so UJ, if you use the picture at the top here, why would you have a positive?
I think it's assuming that like there is it's like assuming that the FG is like I'm thinking it's just F equals FG.
Yeah, instead of a negative there. Then if you assume that, if you just assume here with the direction here being opposite, right? Then you'll say F equals Fg, then you'll have no negative there. Then it will be positive there. Because we don't have a picture. We can't actually assume that that's a picture because that's for number 4. So I wouldn't assume that. But if there isn't, I guess we'll have to assume that it's positive, and this will be our net force equation then, right? So if it is suspended, then you go Fe minus Fg equals 0. Then you'll end up with Fe equals Fg, which is being positive, and you'll have a positive charge right there. Okay, so unless you have a picture, you can't really tell. Okay, question B. How many electrons would need to have been lost or gained? So if we are gonna have a positive charge, it's gonna be gained, right? So we just take that and you divide it by the charge of 1 electron, which is 1.6 times 10 to the negative 19. And you get, do you have 116? Okay, 116 electrons lost. If you gained, if it's a positive charge, that means you would have lost electrons. Okay, so what about C? Suppose that the oil drop is now experiencing a downward acceleration. So now it's gonna go net force down, right? So you still have your Fg down, your Fe up. So you got net force going down. Calculate the electric force. Okay, so calculate the electric force. All right, so our net force now is Fg minus Fe. Okay, so to calculate the electric force, it's gonna be Fg plus net force. Okay, so let's put in our mass here. Mass of 8.22 times 10 to the negative 11 times 9.8 plus, what's our Q? 4.36 times 10 to the 7, and the charge we found to be 1.85 times 10 to the negative 17. Okay, so let's enter all those numbers and see that. Can you guys try this, please? 8.22 exponent negative 11 times 9.8 plus 4.36 exponent 7 exponent negative 17. And I got 1.6 times 10 to the negative 19 newtons. Okay, now that answer there, if you guys calculated this correctly, this should be the correct answer. I'm suspecting this was just the net force. So let me just double check that.
It's the net force minus the Fg.
Yeah, because I think it's still assuming that the bottom is positive. So
Mm-hmm. Yeah, this picture is, there's no, we don't know what the plates are. See, the question that we did earlier from number 2, we know the plates are positive on the bottom. So assuming, it looks like we're assuming the picture is the same. So then you'll get FG plus FE is the assumed equation here. So if you did that, then your FE is going to be your net force minus FG, and you get the answer on the paper, which is 3.05 times 10 to the negative 10. So you're assuming the picture is the same as that on number 4, right? Which is what we did for number 2, right? Okay, so that was kind of a vague question. I would probably give you a picture so then you know what's happening, okay? So that one here is, again, assuming that the picture is the same as number 4. Then this will be the net force equation.
The other one that we tried out, the 1.61 times 10 to the power of negative 19.
Mm-hmm.
I keep on just getting it to 10 to the power of 9, negative 9.
Oh, really?
Yeah.
Hmm.
I'm worried that it's my calculator.
I'm not sure. Okay, so then this will be the case if you have the parallel plates looking like that. It's the same as number 4. Okay, so then I will take this out and we'll use this equation, and that will give us that, and it's gonna go down because it's accelerating down. Okay, you guys want to try the last one for D? Now you're accelerating. Suppose now you're experiencing a downward acceleration. Calculate the electric force. So now we're going to put it into the net force here of that acceleration. So it's the same thing. So you're going to calculate the electric force. Your net force then will be different. Okay, your A here is going to be changed to 17.4 meter per second squared, and that will give you the answer here of 6.2 times 10 to the negative 10 newtons. Still going down. Okay, if you guys want to try the last question, okay, just plugging in. So this will be, your net force will be MA minus MG. So when you change your acceleration to 17.4, you're gonna get a larger force going down.